Okay. Yeah, we're going to start on time, 4 o'clock. Yeah, welcome to our first webinar with the title Preventing Hacks and Business Losses, Reverse Engineering Explained. My name is Nils Albartus, and I'm here with our co-founder from Emproof, Tim Blazytko, and we will talk about different aspects of reverse engineering embedded system today. This is here, okay. This is somewhat our first, big webinar in our embedded security webinar series that we have planned. And so we as Emproof plan to offer different webinars, some with our partners, some just with our experts, about various topics in the embedded security landscape. And today, Tim and I will be giving a high-level introduction to reverse engineering and showcase how different protections basically work. And followed by that, in April, we will give a webinar about CIA compliance, so the Cyber Resilience Act, with a special focus on embedded security in that sector. And we will do that together with our partners at home, who are experts in the domain of compliance and regulations. And that webinar will take place, roughly early April. We haven't fully set that date yet, but we will announce the upcoming dates on our LinkedIn page or in our newsletter. So if you want to stay updated, make sure that you sign up to those. In June, we will do a webinar about defense sector security with our partner DDCI, who are one of the leaders in safety critical real-time operating systems in the avionics sector. So if you want to learn more about that, that's going to happen in June. In August, we planned on doing one about the risk of exploitation. So this is mainly about the risks that are introduced by memory unsafe languages like C and C++. And then in October, we will take a look at how Python code can be detected. And like I said, if you want to stay up to date on when exactly these webinars are taking place, make sure that you follow us on LinkedIn or you subscribe to our newsletter. It's not happening like it should. All right. So before we get started, a bit about us.
Yeah, hi guys, I'm Tim. I'm the chief scientist and head of engineering at Emproof, and I'm also one of the co-founders and responsible for the technical security architecture and the engineering.
Right, and I'm Nils. I'm the interface at Emproof between the commercial and the technical side. And before I joined, I did my PhD at the Max Planck Institute for Security and Privacy in the Ruhr University in Bochum in the area of hardware and embedded security with a major focus on hardware reverse engineering. So as you can already tell by Tim's and my profile, we have a lot of knowledge in the domain of software and hardware reverse engineering, which is both very important when you take a like a whole look at embedded security and reverse engineering, as you need to have both views, so the software and the hardware view present to have like a good security for the whole system. All right, so today we are going to talk about different threats that embedded devices face in the embedded world. And therefore we are going to start with a short motivation where we will detail some real-world attacks that recently have occurred. And then followed by that, we will take a look at the attack flow of embedded devices, so a more generalized structure. And we will start from firmware extractions and then moving on to software reverse engineering, which will be the major part of this webinar today. And then finally, in the end, we will look at different protection measures that can counter these attacks. So in this case, different we will showcase some that reverse engineer use to do the software reverse engineer approaches that reverse engineers take. So let's start with an overview of the different attack vectors for embedded systems. And I want to start by answering the questions, why people would even attack embedded devices. Yeah, and one example that we've seen is that people reverse engineer the device to make sense of what makes a product so great or so unique, to either steal particular algorithms or clone the device. And from a business point of view, this is a major concern, yeah, as this will result into losses of resource and development costs, and also the competitive advantage that a company has, because they have a device or software that runs 10 times faster, can like do 10 times more things than the competitors' devices can. So it's really important here to protect the IP of a company, of a product, so that all these valuable R&D costs are not lost. Then embedded devices also often serve as an entry point for further attacks. So by using them to infiltrate other parts of the systems, which then can result in like data breaches, eavesdropping, or even corporate espionage. And moreover, people have hacked embedded devices to, for example, unlock paid features. And we're going to take a look at that in 1 second. And yeah, so there's always like this financial motivation. And all of this is something we've seen or heard before in the past, yeah, on different levels of the systems, on the embedded devices, but also like on servers. And most of these attacks are often enabled because of one big flaw, which is often very poor software security. And in the embedded security landscape, people take care of a lot of things. So starting with network security or hardware security, or even like physical security in form of like external anti-tampering measures. And nowadays, most devices use even like cryptography, which is great, and it's an essential and crucial part of almost every embedded system. But especially when it comes to cryptography and encryption, this is not where things go wrong. Yeah, and attackers will not start attacking our mathematically proven secure crypto algorithms, but rather they would start looking at the implementation and all the stuff around it. Yeah, and one vector that is often neglected here by all of this, and which has the potential to bypass all of these other verticals that we have up here, is binary software security. And software in many systems is the foundation to provide a certain level of resilience. And if this foundation is not properly protected, then this is the potential to cause harm for all other verticals that you can see up here. And this is a great visualization that my former office mate during my PhD time always liked to use. Yeah? And I think this picture is from the university in Bielefeld, and it's such a great way of visualizing the problem with security. So imagine the barrier that you see here in the middle of the road is all these great security verticals that you already have in place, like hardware security and encryption. And now imagine that, you know, if you fail to have like a whole system approach to this, yeah, people will just circumvent these measures by, in this case, literally driving around it. And when you map this to the embedded security, here a major issue is the poor software security, which allows people to circumvent all these other verticals that we've seen before. And the issue here is often rooted in the fact that probably 90 or even 95% of embedded devices use C or C++, right? These are these memory unsafe languages. And as we all know, especially deeply embedded devices lack basic exploit mitigations. Yeah, and this is why it sometimes feels like these embedded devices are stuck in the 80s, because buffer overflows and other memory safety issues are still a thing, yeah, which is a problem. And in addition, reverse engineering of the software is a similar problem, which is often completely underestimated or even like forgotten by most security experts. And it can be used to identify weaknesses in the device or even to circumvent other security verticals. And remember this, and in a couple of minutes, you will understand why this is an issue and how people are able to circumvent these things with or by exploiting different software security issues. But I want to give you some examples from the real world. Yeah, and you might remember these headlines from a couple of years ago So this one here is about Tesla. So Tesla's new Model S and X have the same battery pack, but with software locked capacity. So what Tesla did here is they built in the same batteries into the cheaper models and lock the capacity via software. Yeah, here's another one. BMW wants to charge your subscription for your heated seat. Yeah, so BMW built in the seat warmer into your car, but you had to pay them a subscription-based fee to actually use it. And I think by now, I'm not sure, BMW actually reverted these changes as they were, as one can imagine, not quite so popular with their customers. But what this usually means is that the internet or hackers in general see these announcements as a challenge to start looking into the security of devices and start hacking things. And what we saw in the case of Tesla was basically that researchers did exactly that. They looked at the software and found some bugs in the software and the secure boot process to activate paid features. In this case, this was not aimed at the battery, but again, at the things like the seat warmer for free. And they did this by identifying some issues in the software, which they were able to exploit, and bugs in the secure boot process. But what these things in general mean is that we usually see a gray market building, where hackers reverse engineer the software to find vulnerabilities, which they can then exploit and then sell these hacks for like a much cheaper price compared to the subscription fee that you have to pay to the vendors. And this cat and mouse game here is decades old. Just think back like 10 to 15 years ago when everyone was still jailbreaking the iPhone or hacking the Nintendo Wii. Most of these things built on software bugs that people identify via reverse engineering and then find a way to exploit them. And wherever there's a financial gain, people will find a way to attack the devices. So to generalize this problem or the procedure, how attackers proceed a bit more. And the attack flow for embedded devices looks somewhat like this. So we have our attacker here on the left, who's looking at the embedded device, and usually the first step is the extraction of the binary from the device, in which we are going to look in more detail in a couple of minutes. And afterwards, the actual reverse engineering of the firmware or software, and people do that for various reasons. So for example, exploiting the device, finding these vulnerabilities to hack or jailbreak them, or even competitors do that because of the product piracy, stealing of algorithms, and so on. So if we are looking at the motivation again, there are several scenarios. So one of them is this intellectual property theft that we've already discussed, so stealing competitors' algorithms. And another one is this vulnerability analysis, which is used to find these exploitable weaknesses in systems. And then finally, we have the piracy and cracking, which is usually about circumventing these paid features or some license checks that are in there, like in the example with the seat heater, where these paid features were activated for free. But to get there, they have to get the firmware first. And in this first phase, the goal is quite simple. They want to read out the software from the device. And how do they do that? Well, so most devices offer like JTAG access, for example, for debugging purposes, which can then often be used to read out the firmware directly from the device. Now, you're going to say that most modern microcontrollers have a readout protection. And while that's true, these readout protections don't always work out like they should. And there are often some ways around it, which we will discuss in a second. But often this is not even necessary. And this is especially true for consumer devices, where the firmware can, for example, just be downloaded from the internet. So think of your printer, your Bluetooth headphones, or your smart home devices. If you go to the website of the companies, you can actually find links to download the most recent software, the most recent update for your devices. So here there's really no need to extract the firmware from the device, as these can often just be directly downloaded from the website. And typically, these are even usually not encrypted. Otherwise, if the devices have like these update capabilities, it's also possible to sniff the network traffic from the device. And by that, you can like dump the firmware as well, or figure out which URLs they are accessing and then download it yourself afterwards. And I just want to give you another example. So for example, for car tuners or car hackers, there are actually a lot of underground forums available where the firmware for the ECUs or other components in the car are just often available for download and shared within the community. Another way of getting to the software is actually because sometimes you're directly shipping libraries, yeah, or part of the software itself to your business partners or to your integrators, so they can integrate your product, your library, your software, whatever you're selling into their products, which gives them direct access to your valuable intellectual property and basically gives them direct access to the binary, and they can start reverse engineering right away. But going back to the readout from the device, and here people are often surprised how easy it is to get the binary out of, read back the binary from the device. And there are several shady companies out there where you can chip your device, and they have like a catalog of different weaknesses for several of them to bypass the readout protection. And the catalog of supported devices is actually quite huge. And these weaknesses are often related to issues with fuse bits or the initial bootloader, which can be faulted or glitched, or even sometimes, which would be more advanced, conducting like circuit editing using a FIP. And additionally, you will be surprised if you Google your microcontroller for known vulnerabilities, especially for like older devices. You find a lot of online tutorials that will tell you exactly how to extract the software from that regarding microcontroller, because people often found weaknesses which they share in like some online tutorials and online blogs or on YouTube. Yeah. So all of this is out there, but I just want to give you some examples of some examples, websites of these companies that actually offer this as a service for just a couple of $1,000, which have a huge catalog of devices available, where you can just send the regarding chip and then get back the binary, and then can start whatever you want to do with it. So now that we've discussed binary extraction, let's look at software reverse engineering a bit more. And we are now at the point where we have the binary. Yeah, so we are basically here in this diagram, and now we need to make sure, or now we need to make sense of all the zeros and ones that we've just extracted. And this usually means that we first have to disassemble the binary for further analysis. So what exactly does that mean? And more importantly, how does it work? So let's look at an example. Yeah. So here you can see some data of the binary that we have just extracted. Yeah, and this is just a very high-level example. And we now have to look at the documentation of that regarding microcontroller to figure out which architecture they are using and how the instructions are actually built for that specific device. So, and we can in this example see that the first few bits are the opcode, followed by the register, and then followed by some constant. And of course, this is a super simplified example, and there are different instruction types within one architecture, but generally this following approach is how it works. Yeah. So here, the first few bytes, or in this case, the first byte is the opcode. So we have, in this case, two instructions, this instruction here and this instruction here. And the first instruction that starts with that 0A, yeah, that is in this case an addition. And the second instruction starting with the 0B in our example is this multiplication. Then, if we continue, we have as next the next byte here is the register. So in this case here we have register 1 and register 2, which is used to write the result of the operation 2. And then we have two constants, so the 0A constant and the state constant regarding operation. And the things that we just did manually here, so piece by piece putting together the instruction, this is basically what we call disassembling. So this decoded meshing code here that we see is basically what is called the assembly code, and this step is called the disassembly. And usually this is not something that we have to do by hand. Yeah, there are tools out there that do that in a completely automated manner, and yeah, this is not something that people have to do by hand, and it's very easy to get from all these fonts or something that is more understandable, that we can use for the remainder of our analysis. And an experienced reverse engineer, so not necessarily me, I'm more for the hardware side, but people like Tim can already learn a lot of things at this level. So like identifying API calls or identifying important data section. But as beginners, this is not really fun to reverse engineer. And this is where tools like decompilers come in. Yeah, and the decompiler, or the idea behind decompilers basically is that they are able to go from this disassembly to like a high level looking at something like this that we see here on the left. We are looking at something which in this case looks like the C-like source and even has the symbols available, so functions or variable names, which is the case if the binary hasn't been stripped before. And yeah, this is basically not something that the compilers do automatically. You have to instruct them to do that. And most people leave the symbols in there. So with the symbols available, we are really looking at a very, very similar C-like representation of the source code that we can use for the reverse engineering process. And this always sounds like a bit of magic, but it's actually pretty standard. And the community behind all this is really, really active and has created really advanced tooling. And there are several open source and also like some commercially available frameworks all over the internet. And I guess the most popular ones that I've put up here are like Ghidra, IDA Pro, and Binary Ninja. Ghidra is actually quite interesting because it's released by the NSA. It's open source, freely available for everyone. So this is a great tool to get started if you ever want to try this yourself. So, but I want to, yeah, before I hand over to Tim for a live demo of all this, I just want to briefly talk about the consequences again. And we've already talked about software reverse engineering itself, but of course we've barely scratched the surface of how attackers actually do this nowadays and what tools they have available. There's like a wide range of things that they can do. Yeah, but consequence-wise, we've already talked about intellectual property theft, so theft of valuable algorithms or cloning of devices. Something we haven't talked about yet is like this key or token stealing, and this is actually where the community is really active. So identifying crypto is one of the things that people have researched quite a bit, and this is actually something that Tim is going to show in a minute, so I'm not going to talk about it too much. But this is something, if you have like hard-coded keys or tokens in your binary or other sensitive data, this is actually something that's quite easy to get out. Another thing is, and this is about what we've talked about in the beginning with the Tesla and BMW hack, bypassing license check, bypassing these paid feature activations. So finding vulnerabilities inside the binary, also like maybe like modifying the binaries to patch these checks away. This is what we call cracking. Yeah, so cracking is a very serious consequence of all of this that is enabled by software reverse engineering. And finally, vulnerability analysis, so identifying exploitable weaknesses, or which can be used to generally undermine the system security. Yeah, and I think, before I hand over to Tim, that I think the site is super important because it shows all these different attack vectors. And when I showed you the slides with the different security verticals like network security and encryptions and so on, it now becomes clear, yeah, by software security itself has the potential to bypass all of these other security verticals that we have up there. So if someone is able to steal the key, it's great that we have encryption, but they have the key, and that's becoming more useless. If we insert like license check activations or something like that, that's also based on like crypto or even like a complex public key infrastructure, but it can be patched away because the license check is just some if query in the end. Yeah, this is related to the cracking. There is like not really great security in there. So all of this can often be bypassed because of poor software security, and it's important to deal with these consequences and have do something on the software security side. But before we get to that, now is first of all time for the live demo, and I will hand over to Tim, who will show you what these tools look like in practice.
Yeah, thank you, Nils. Let me start by sharing my screen. Can you see it now?
Yes, we can.
Awesome. Okay, so let's start by taking a look at a simple C source code. So what we have here is a function, which is the main function, and it hard-codes a symmetric IS key. IS is a well-known symmetric cryptographic cipher, and you shouldn't hard-code your cryptographic key here. However, this is something we usually see in customer binaries quite a lot. So, but now let's see like a token. Let's like a look at that. We have it starts like 60, 3D, EB, and so on. And then the function prints the hard-coded key and then performs some encryption of the plaintext, calls a cryptographic cipher down here, which gets the key as input. And then finally, we print the ciphertext. And if we execute it, it basically looks like that. So we compiled it down to a binary, and then we can execute it. And then we see the hard-coded key, which is a 60, 3D, and so on. And then the ciphertext for the Hello World example that we had encoded with this key. Okay, now the question is, what can an attacker do? And the first thing would be to figure out that this is really binary by, for instance, using the file command. We don't have it here. So the file command, here we have it, tells us it's an executable file for the ARM64 architecture. Okay, then we go to a website like, for instance, guidera-software-reverse-engineering.org and download the free software reverse engineering suite, Ghidra, that is developed by NSA, which has been just explained by Nils. Once we have it installed, we can open it like here, and then we can import the binary. So we go to File, Import, and then we navigate through the location like webinar and then the ES demo. And then it also tells us again it's an executable linking file format for the Arch 64-bit architecture. So we press OK. It analyzes the file, and then we can double click on that. Then it takes a while. It asks us how to analyze it. We just leave it as default. And then we see different windows here. The most important window right now is the one in the middle. Here we see the things Nils was just showing us, the so-called assembly code, where we have here some byte sequences, which are encoded instructions. On the right side, we see the human readable form of these. the so-called assembly code. And now an expert reverse engineer could start analyzing that. However, as Nils was telling, it's not about being an expert here. We want to be able to extract information from the binary without being an expert. So this is why we will switch to the right side of the window, the so-called decompiler. If we click to this function main here, we will see on the right-hand side that we get something which looks like source code. It's not exactly the same source code as we just saw it in the original file, but it's close enough. We see that we have the function name main. We see that we have some variables here like the ciphertext, but the most important things are these things. This actually is the cryptographic key. We can check it if we take a look at the last bytes here. The 60 3D EB10. If we go back to the shell, we'll notice it's exactly that, 60 3D EB10. So we can not only see the key, so we can, it continues with 15 CA71. Here we have then 15 CA71. It's just the opposite order. And so we can basically hear this is a cryptographic key. If we scroll down, we then see again that we call this AES function, that we encrypted, and here we have our print of the hard-coded key, then our string, this is a secret message, and then somewhere where we print this ciphertext. So basically here, the software reverse engineering allows us to see the tool and to analyze the binary and even get a high-level understanding of that, including observing the cryptographic key. Also, we are not reverse engineering experts, so we don't have to look at this code. We can just look at the decompiler output and get at least some understanding of what's going on here. This is a threat we want to protect against. And with that, I'll bounce it back to Nils.
All right. So that's pretty scary stuff, yeah. Let me go back to the slides and let me go back to where we ended. Okay. So basically in this live demo, Tim showed us how to load a binary into Ghidra and then how to analyze the binary with the decompiler, but also the assembly code, and showed us how, in this case, by using this standard, was it OpenSSL, Tim? I think it was OpenSSL.
Yes.
Yeah, OpenSSL AES implementation, and yeah, showing how these calls can be reverse engineered and how the key can be identified. So before I continue, Tim, we have a question actually, which I'm going to hand over to you. So the question is, what about compiler dependencies during decompiling? So I guess how can these be resolved? And yeah.
Well, actually, we see everything which is in the code, like the user code and also external dependencies and so on. It depends if you see external dependencies or not, like if we see the actually API call that goes to an external function, or if we include the API call inside of the binary, like if it's statically linked. This depends, but usually we see everything which is user-provided code at least.
Okay. If there are any other questions, let us know, and we have the chat open. Okay, but continuing with the talk, yeah, we're going to look at how we can protect against this. Yeah, and this basically brings us to software hardening. So how can we defend ourselves against these attacks from the reverse engineering side? And luckily, for us, there are several things that we can do. And one thing is the actual reverse engineering protections, which per definition safeguards software from unauthorized analysis. And here techniques include different things such as code obfuscation and data encoding, or anti-debug and emulation measures, because it's not only important to prevent like the static side. So far, we've only talked about the static side, but we also need to protect it against dynamic threats. So if people are using a debugger or like an emulator, this is also something that we need to protect against, because reverse engineer uses to make sense of the binary. But yeah, anti-tamper measures are also important to ensure that the binary has not been patched or modified. So for example, because someone simply removed the license check, so we need to insert measures that ensure that the binary has not been tampered with. Something that we're not going to focus on today, but I just want to mention is exploit mitigation, which are these security measures to block attackers from actively exploiting these vulnerabilities. And these exploit mitigations, they are not usually about fixing the bug inside the code, so not fixing the buffer overflow, but it's rather about preventing the consequences. So making sure that an attacker cannot simply use these vulnerabilities and take control. Some techniques that are important here, especially for the embedded sector, and this is where most open source compilers fail to deliver this, include things like stack canaries or control flow integrity. You might know it, it's in short form called CFI. But this is not something we will cover today, but this will be covered in another webinar in more detail. So reverse engineering protections. One super important one is code obfuscation. And this is usually used to increase the code complexity to impede the reverse engineering process. And when it comes to obfuscation, it's always important to not only deploy just one technique, but actually several that interact with one another. So it becomes for the attacker kind of like peeling an onion, where you might have cracked like one layer, but there are like 20 more layers to come. And ideally, you have to crack these layers simultaneously. So you have to make sure that these different techniques all depend on one another, and then it becomes really, really hard for an attacker to actually do the reverse engineering. And this is just a very simple visualization of how obfuscation works. So on the left here, we have just some electric grid where everything is like very clear and where all it's like directly visible where the wires are going. And if we would apply obfuscation to this, it would look somewhat like this, chaotic and really hard to understand. And you have no idea what's going on and where your wires are going. So this is really what obfuscation is about. And of course, maybe this is not a super good obfuscation because maybe you can figure out what's happening here in a couple of hours. But generally, this is what obfuscation is about, making it really, really hard for reverse engineering, for a reverse engineer to understand what's going on. But as mentioned before, code obfuscation will only get you so far. We also need to prevent debugging, access, and emulation of the binary, because these are tools that can reveal many information for an attacker. And combining this with anti-tamper is crucial, because otherwise the attackers will just modify the binary, not only for the patching, so not only because they want to or the cracking, because they want to remove checks, but also they would use this to conduct their analysis and just, remove some things around, make the binary simpler for them to analyze. So this is also something that needs to be prevented. I still see the intro slide. That's not great, but I hope that's not the case for everyone. Can someone confirm if they see the current slides, or are we stuck on the intro slides? I will just continue and assume that the slides have moved on for the rest, hopefully. And these things that I've mentioned before, so code obfuscation and anti-debugging and anti-tampering measures is basically what we can do at Emproof. So we've developed a software which is called Emproof Nyx, and this is our binary transformation framework, which people can use to protect their software. So Nyx offers all these great mitigations, and it's actually pretty easy to integrate. So the note in the chat is that you have to press the sync with the presenter button, and then you're taking to the slide where we are currently at. But back to this, yeah. So with Nyx, you can take as input the unprotected binary, yeah. So basically, basically here the unprotected binary, and yeah, apply via this configuration profile different protections that you want to be inserted into the binary. And then both of these things are input for Nyx, and out comes the protected version. Yeah. And here the customers have a lot of flexibility and customizations. So they can like they can blacklist certain functions. For example, if we're like talking about an airbag software where every clock cycle counts and absolutely no overhead should be added for like safety concerns, you can say that you want to exclude this function or address space, but at the same time you can like apply very different and a lot of our transformations, our security transformations that we have available to certain functions that are important for you and where this protection is really needed. So you have the option to either protect the entire binary or only parts of it by whitelisting or blacklisting functions. And we have several customers who are already using our solution, and one of the best things for them is that they don't have to develop this in-house, because these things are actually not only expensive to develop in-house, but they also require a lot of experience, and not only experience in like software security, but you have to know the other side of things. So you have to know how the reverse engineering works, and you have to have a lot of experience in that. Otherwise, if not done properly, the desired functionalities that are being built for this don't really provide the desired protections for the reverse engineering side. Yeah, and additionally, some of the things that we can offer, which is mostly true for the exploit mitigations, like the protections for the stack canaries and the control flow integrity, will be part of upcoming regulations, like the European Cyber Resilience Act. So Emproof Nyx can already help you tick some of the boxes when it comes to like attack surface mitigations. But this is something we will discuss in the next webinar in more detail and won't be covered in that much detail today. Yeah, so I just left this slide in here. This is an overview of our main offering. So on the left, we have the reverse engineering protection, which can be used to protect like IP, so valuable algorithms, but it can also be used to hide keys, which is what Tim will show in a second. So how can these keys that he just identified using the tools like Hydra be hidden so that they are not so easy to find by a reverse engineer. But we also have here on the reverse engineering protection side, again, these things like anti-debugging and anti-emulation detection and also anti-tamper. Yeah, and for the hacking protection, which was about the detection and prevention of these exploits that are in there due to the memory safety issues, we have different exploit mitigations available, which will help to prevent different vulnerabilities, and for example, like malware or privilege escalation attacks, and can be inserted just by a click of a button into the binary. So Tim, I will hand over to you again for the live demo of what our tool looks like in practice.
Thank you. Now you should be able to see my screen again.
Yes, I can see it.
I hope the others too. So now we basically will use Nyx to protect this attack of the binary. So we remember that we just saw the key in the background here, and this is something which we don't want to have inside the decompiler anymore. So what we do is we take our demo and apply Nyx to that. So for that, we write a profile.toml, which basically adds one of many obfuscation schemes. We choose one which is called as arithmetic obfuscation or instructional substitution, which basically replaces simple computations with large complex formulas and applies this to the function main. And these are options, how complex the obfuscation will be. And we set it to some options that for demonstration purposes that are very high, such that we can see a lot of differences. And what you would usually do is you would apply many small-scale solutions that have a similar effect but don't look that impressive. So what we do is we have this profile, and then we call our tool Nyx. Nyx is provided here as a Docker container, which we can call using a makefile. If we can do make protect, we basically run the Docker container and provide it as input file our file to the ES demo, so our binary. Then we specify the operating system, like Linux or bare metal or Windows, the processor architecture, in this case it's ARM64, and then just the profile, which we took a look at beforehand. And this profile basically specifies which obfuscation techniques to provide, what are overhead boundaries, and so on. And finally, we provide the output file with -o, like it's asdemo.nyx. This is basically just the command line which is run. So what we do is we do make protect. And now this takes around 40 seconds. What happens in the background is that we read in the binary, analyze it to know where's code, where's data, what kind of code, how's the code structured, how complex it is, what are the protect-worthy parts in that, and so on and so on. And then we come up with a strategy of how to protect that, where to put the protected code, and merge everything together. And finally, we will spit out a hardnet binary. It should now be in the next seconds. We should just finalize it. And then we have the hardnet binary. And this hardnet binary will basically work exactly the same as the unprotected one, but it will be significantly harder to reverse engineer. So now we see that the instruction substitution has been applied, and that in this case the code size increased. As said, we made it to be very complex in this case, such that we can see invisible effect. And then we wrote the transferred binary to this file. So now let me first demonstrate that it works exactly the same. I first have to make it executable, like that. And then I can execute it .nyx. And just in comparison, I can execute the original file again. And then we see the observable behavior is the same. Like in both cases, we print the cryptographic key and the ciphertext in the protected and unprotected version. So this is the proof that it works the same. The question is now, how does it look like if we try to reverse engineer that? For this, similar to this binary, where we loaded it into Ghidra and we're able to see the code here, I will do the same thing for the protected binary. So I will do file, import file, choose this protected version here. Okay. Then double click to analyze. Yes, analyze. And then we go to the same function, main, and we already see that the code looks different. we see that there's a lot of more code, and it's also different. Like if you compare it with the assembly code here, these are just a few lines, and we see some things, and here it's just significantly more obfuscated. However, this is not the real magic. Let's take a look at the decompiler, what the decompiler thinks. And the decompiler thinks that there are a lot of computations which do things, and here we don't have any clue anymore what's going on. So the key itself is protected. We still see the print to the hard-coded key, but we don't see the actual key anymore. We see a lot of large list of computations which compute the key at runtime, for instance, and with some arithmetic manners, but it's now not visible for us what it's the actually key. While at the original binary, we can just read the key like this is it, this and this. And this is nothing we see here. So this is how obfuscation with Emproof Nyx would work. The question is, can you also play around with on your own and learn some of the things? The answer is yes. If you go to our website, like emproof.com, you will find in the right corner something like try our demo. If you go on here, you can choose if you want to do a IP protection demo or a exploit mitigation demo. In this case, we do IP protection. So you can click on here, and then you get a guided tour. You get an idea how to use that you can, for instance, build the source code here, then look at the unprotected code, and then protect it, and so on. And you can also furthermore get an explainer what the obfuscation does. So, but let's start first. So here, for instance, we can choose that, for instance, we can want to practice an algorithm called RC4. And here we can see the source code, again with some hard-coded key. And then we can compile it. And if you press compile, it runs the compiler in the background. And in the middle here, we then will see the assembly code, the same thing we saw before. We can also take a look at, for instance, the decompiler output, and then we can see the decompiler code. It's basically some similar thing to Ghidra. Or we can look at the graph flow and see how the actual code is structured. This is also a possibility. And now we want to obfuscate it. For that, we choose one of the code transformations, which would be equivalent to writing this toml-based file that we just took with say before. And then we go to protect with Nyx. And then it does its magic again. And after it's finished, we see on the right the protected version. And looking at the graph, we already see the graph is significantly smaller because the code doesn't know anymore where to go. If we then take a look at the decompiler output, for instance, we also see that the code looks more complex, and down here it doesn't really know anymore where to go, while here we actually can see the original code. So, and finally, in the disassembly, it also looks different. So this is the online demo you can play around with on your own if you go to demo.emproof.com. And also on top of here, you have some resources where you can learn more about software reverse engineering, basically the things Nils showed in the beginning. And also, if you want to learn more about individual obfuscation schemes, you can go to IP protection with Nyx, and then you get some primer about how Nyx works and also how the obfuscation schemes work that Nyx is applying. This is the online demo, and yeah, go play around with it on your own if you are interested in that. And I think now we are done, and now we are up for questions.
Yeah. Thank you, Tim. We already have one question. The question is, do you have a TARA in place with the applied security hardening, which shows reduced residual attacks? So we have several things we can offer in that area. We have a pen testing report that we are happy to send out on request, where we have pen tested the different features that we have by an independent company. They took a look for like, I think it was 3 or 4 weeks. And then, yeah, really tested everything, all the security that we added to the maximum. That's something we can offer. Help our customers. The Cyber Resilience Act. That's also something we can send out. And for the exploit mitigation, we have a detailed document available, which will show you which memory safety issues we can help you fix in regards to which, or with the help of which security transformations that we have available. So these are information that we are happy to send out on request. I think the best way to reach us is either directly reach out to Tim or me, or email us at contact@emproof.com. So Tim, I also have a question, because this is something we regularly hear from customers. We've seen in the demo that obfuscation is not free, yeah, but I want to know, like, what is the general overhead, or it's a question customers often have, of the different the different reverse engineering protections, especially in the embedded space.
So usually obfuscation is applied in the desktop area where we have something like games or large multimedia libraries, and their overhead is often a factor of the entire binary, like factor 5 or something like that. However, in embedded, there's no way you can do that, because there you might have just some ROMs with some limited kilobytes, like 64 kilobyte ROMs, for instance, in the worst case, where 50 kilobytes are used. So in this case, you can't do many factors like that. So what we do is we break it down, that we apply something around 10 to 15% overhead, depending on the configuration. So like you can, for instance, configure in the profile how much overhead you actually want to have, and then Nyx decides automatically where to apply things and what to apply things, so that you meet the overhead boundaries.
Yeah, and I just want to point out that this is basically part of our secret sauce that we didn't show in the demo here. Yeah, so Tim just showed one of the things that we also have available on the online demo, but we of course have bunch of transformations that we can add to a binary, which we are happy to talk about after we get into more details of a project discussion. So are there any more questions from the audience? If not, I think we have almost reached the end of the webinar anyway. It's now exactly 5. Yeah, maybe just one last question, Tim. In your personal opinion, do you think beginners are able to reverse engineer a binary, or is this something only experts can do?
No, absolutely. Like, of course, you won't understand every detail and every bit. And if it's very large, you might have some problems in navigating in there. But as we have seen right now, you can at least fire up Ghidra or some other tools and get at least a high-level understanding of some part of the binaries without knowing assembly code or without knowing much about low-level security. So the answer is, it depends, but to some extent, absolutely.
Okay. All right. I think that's a good way to end this. And we will have, as mentioned in the beginning, the next webinar coming up in April, which will be about CRA compliance and upcoming regulations in that domain that people have to adhere to, especially in the embedded sector. And what does it mean for you as a product manager, for example, and what things you have to consider to be compliant with these upcoming regulations. And with that, I want to thank you for attending and see you.